Okay, hi guys. Let's get started. So I imagine most of you have attended the first two workshops. We will be using some kind of background information. But before we get started, today's idea and today's topic that we're going to be discovering is linear regression. In the past, the first workshop was essentially an introduction to what machine learning is. The second one was a deeper dive into something called classification, which is why we studied k-nearest neighborhood. Anyone remember all that? Okay, in case we need some background information, in case you feel stuck, in case we discuss something that we've done in the past, just let me know and I'll brief you over it. Okay. So the first thing, what's your name? Jaden. So Jaden asked me where we can access all the resources and all the recordings. So in case you're not able to make it to one of our workshops, we have everything up on that tiny URL. Can you open that for me?
Oh, wait, this one?
Yeah, the first one.
The first one?
Yeah.
Okay.
So this essentially is what we at ACM called an asset cluster, and this is from our previous quarter. We're going to be making one dynamically for this quarter as well. So this has access to all of the slides, all of the code demos, which we shared, which you asked about, and all of the recordings. So some of them are from previous quarters. We do beginner track every quarter. So we've linked you to the best possible resources in case you're not able to make it. Additionally, if you feel like you've been watching a recording and you still need some help, if there's something you don't understand, usually the slides are pretty self-explanatory. But in case you don't, feel free to reach out to us. Are all of you on our Discord? If okay, so what I'm going to do is, okay, at the end of this workshop, I'll send you a link, but it should be on our Instagram. So our Instagram bio has a link feed.
That also is expired.
That is expired, but I will look into that for sure then. Okay. Of course. Go back.
Okay.
I'll just give you all a moment to take this down. Also, another logistic thing out of the way, we have something called the ACM census, which is where we try to understand what kind of people come to workshops, what you want us to do with workshops, how we can play around with it a little more, how we can tweak it to something that you might like. So fill out the ACM census. There's also a raffle that you automatically get entered into when you have some chance to win interesting prizes. Does everyone have this? Can we move on to the content? Okay, sounds good. So like I said, we're going to be looking at linear regression today. So we're going to start off with a motivating example, look at some hypotheses functions. We'll do some math, and then we look at ethics, and finally we'll do a code demo. Okay, we're going to try and make this as interactive as possible. So if you feel the need, if you have any questions, feel free to shout it out, or of course raise your hand and I will call you out definitely. So last workshop we did something called classification, right? And here's what classification means. Actually, can someone explain what classification means? Just a generic idea of the word. What is classification? Yeah, that's the key word. Okay, so classification is categorical. So say I'm given a data point. Say I'm given an image, okay? And I want to tell you if that image is a cat or a dog, right? So those are my two categories. Those are the two bins, and I will be classifying that image into A, a cat, or B, a dog. Now, of course, that can be various categories. That can be an n number of categories, but that is the general idea of classification. What we're going to be doing today is regression. So in classification, we're working with categorical data, and in regression, we'll be working with continuous data, right? So the example that we're going to look at, can you go to the next slide?
Yeah.
Okay. Yeah, I know it's midterms week, and this is the last thing you guys are going to be talking about, but this is something that all of us will understand. So essentially, what we're going to try and do is predict how well Joe Bruin is going to do in his midterms. And the looks of the photo, it doesn't look like he'll do very well because he's at poly. And it's empty, so he's probably wasting his time, but we're going to try and predict how well Joe Bruin is going to do on his midterms, right? So this is an example of continuous data. I'm going to come up with a random number, okay? This number can be 97.5684. It can be anything whatsoever, right? So this is continuous data. Do we have any questions so far? Okay. Okay, so here's the problem, right? We're going to do something called the midterm score prediction. Now let's think about it this way, okay? What information about a student do we need to predict how well they're going to do? Okay, if I tell you that, you know what, you want some data to predict how much I'm going to score on my midterms, or Joe Bruin is going to score on his midterms, what kind of data would you want? Give me any example. Yes. previous grades in previous classes. Previous grades in previous classes. That is a fantastic example. Yes.
How much time they spend on studying?
How much time they spend on studying? Can anyone think of more? There are plenty of these. GPA. Well, yeah, GPA definitely tells you how good a student is and how well they are going to do. Anything else? On one particular exam, how can I know how well Joe Bruin is going to do? Yes. How other students do. That correlates with exam difficulty. Anything else? Now, of course, it can be anything whatsoever. It can be the amount of sleep you got, the amount of video games that I played before the exam, right? It can be anything. All of this data can factor into how well I do in my paper. So this is what we call features, okay? And in the past workshop, we did features and targets, right? Features are essentially the things that I am provided with. So a feature might be the things that you just mentioned, right? How much sleep I got, how many video games I played, what the GPA of the student is, right? Those are the features. And now we're going to be looking at something called the target. The target essentially is the midterm scores that we make, right? So based on these features, I'm going to be predicting a target for Joe Bruin's score. Next slide. Right. So this is pretty much what it is. The midterm score is our target, essentially what we desire to predict. Okay, so let's talk about this. You get it? It works. Sorry. So the relationship between each feature and the target, right? So you gave me some feature examples. Okay. Now, how do you think they correlate to the final exam score, the midterm score? Okay. How do you think they correlate? So if I study more, I'm going to get a better grade, right? If I sleep more, I will probably get a better grade. You know, if I go on 1 hour of sleep, unless I'm on a Red Bull or something, I'm probably not going to do as well as I would if I were on 10 hours. Right? Similarly, there are some things, say amount of video games played before, or the parties that you went to before the exam. Maybe you're hungover, okay, and you don't do as well. So that has a negative correlation with the target. So these features can be of two kinds, okay? It can be ones that bolster the score or reduce the score. And we'll be discussing this as something called weights, which we will get to in a second. But does anyone have any questions at this moment? Are you clear with the ideas of features, targets, and the negative or positive relationship of every feature with the target? Hands up? Okay. Yeah.
Just things like, let's say for sleep, what hours is
Mhm.
let's say little sleep is like unreasonable, or like much sleep is too much. So
Yeah.
it's still a linear difference.
Okay, so essentially what we do is we work with a lot of data sets, right? So we have a lot of data. Now, some of it might say, 10 hours of sleep is bad. So there's going to be a sweet spot, right? So we give the weight accordingly, and that is something that we will discuss in the next function that's on, okay? So don't worry about it. Next slide. Okay, so this is how we represent our data, okay? So this is what the data set looks like, okay? I asked you what kind of data set you need, and these are some example features that I've taken. The homework average, the study hours, of course, homework average. If I'm getting a 0 on my homework, I'm probably not going to do very well in my final, right? The study hours, the amount of hours spent in lecture, which isn't usually a lot. And the midterm percentage, this is the target. So these are the features, and this is the target. And this is every individual case, okay? So this is one student, he got a 70%, 10 study hours, 18 lecture hours, and ended up with an 85%. Second student, she got a 95%, and so on, right? Is that clear? So this is what the data set looks like. We're working with features and the target. Next slide. Next slide. Yeah, we call this Y because what we're going to do now is we're going to delve a little bit into the mathematical interpretation. This is going to be very surface level initially, and then we'll sort of see how it goes and we'll cater it accordingly, okay? But for now, we're going to call the target Y. Cool? Next slide. Okay, so at this moment, let's formalize everything we've brought. Okay, this was a very intuitive example. This, of course, is not how it generally correlates to what linear regression looks like. There are a lot of nuances that we haven't discussed, but this is just the gist of what's happening. Let's formalize this, okay? So there's something called a hypothesis function, okay? And this is the word you're going to be hearing throughout the beginner track series, throughout advanced track. This is a very important word. Essentially, it's the function, right? So I'm going to be giving in these features, okay? Everything you see in the bracket is the features that I'm going to be inputting. And based on that, I'm going to run this function. Okay, what does hypothesis mean? Can someone just tell me? What? Yes, educated prediction. educated prediction. So essentially what we're trying to do is we're saying that this specific function is going to give me the final midterm score. Okay. This is our educated guess. Now we're going to try and figure out what this actually is, what the actual mathematical definition is. So there are input features, which are the values we plug into y hat. We call this y hat. And yeah, this is the function that we're going for. Okay, we have to determine y hat. We have to make our hypothesis into the actual function. Next slide. Okay, so essentially this is something we've already gone over, but we look at all these features, right? How important do you think all of these features are? So before we discuss a positive correlation and a negative correlation, right? Now we're going to discuss how important all of these features are. So, okay, which ones of these do you think are more important or less important? Let's do more important first. Which ones of these do you think are extremely important, more important than the others, relatively important? Yeah, A and B and C. These are some of the things. So we've obviously listed this in a descending order of importance because the amount of chocolate you consume is probably not going to make you do better. Otherwise, I'd just be binging dairy milk. But what we're getting at here is features vary not only in positive and negative correlation, but they also vary in terms of importance, right? So we're going to be discussing something called weight stuff. Okay. And before we delve into that, does everyone know the equation of a line is? Can you say it out loud? Y is equal to mx plus b, right? So that is essentially what we call the slope-intercept form. There are various ways to represent a line, but in linear regression, we're trying to find the line of best fit. So given all these features, I want to make a prediction. So at every single point, based on certain features, I'm going to have a certain result. Okay, so we're going to be working with lines here. Let's get to it. But does everyone get the idea of importance of features? Perfect. Okay, so this is where weights come in. Okay, we discussed that these features can be positive or negative. So we're just gonna put them as a plus or a minus. So this is what we're working with here. Okay, so for a second, let's just disregard this section. Okay, in a 2D plane, what we have is y hat of x is equal to b plus w1 x1. Let's remove the ones. We have b plus wx. This essentially is mx plus b or mx plus c, right? Where w is the weight that we're giving to this specific feature. Okay, so if it's an important feature, I want to be giving it more priority, right? It should be able to govern my function's result better. And we have something called a bias, which is essentially the intercept. Okay, but the thing is, we don't only have one feature. We have hundreds, thousands, we can have 10 million features. Okay, machine learning data sets that we work with right now have tons and tons of features. So we generalize this as y hat of x is equal to the bias plus the weight of a specific feature times the feature. Okay, the feature is going to be different for every data point. And we continue to do this for n data points. Is that clear to everyone? Any questions? Okay, so this is how we're going to work with it. Now, again, what we've already talked about, these weights can be negative. Okay, if I am playing too many video games, I might say, you know what, I'm going to give this x2 a -2 weight. What that means is, well, this thing is going to negatively impact my target, and I don't want that happening. So I will account for that. Now, what we want to do is find the best possible weights for our equation. Okay, and these weights keep changing. So how an ML model works is it works for data sets, and it continuously changes this hypothesis function. Okay, as it's training using the data. Okay, yeah. The B is the bias. We'll get to it in a second, but it's essentially the intercept that we talked about. Okay, yeah.
Sorry, so do weights factor in correlation?
What do you mean?
So it says that the weight can be negative.
Mm-hmm.
Is that the correlation itself, or?
Yeah. So when I'm saying that, you know, for instance, time spent playing video games is negatively impacting my midterm score, so I'm going to give it a negative weight. Does that make sense?
So weight includes correlation as well?
Yeah. The weight includes correlation. So I take tens of features. Let's go back to our example for a second. Okay, I can see some doubts here. So going back to our example, let's disregard the bias for a second. No, go back to the word. Disregard the bias for now. Okay, now x1 can be number of hours spent studying. Okay, and that's a good thing. So it's going to have a greater weight. That could be 10, that could be 20, that could be based, it's going to be relative to the rest of our features. Okay, for the same thing, if we have something positive, negative, and then we get this function, and then at the end we add or subtract the bias. Is that clear? Does that make sense? Okay. Next slide. So, well, this is pretty self-explanatory, but this is essentially what we've already talked about. We take the input features, we give each of these features a weight, and then at the end we work with the bias. Okay, and that essentially is our linear regression model. Next slide. Okay, so this is just a mathematical representation of pretty much the same thing, but here is what we're doing. What we do is we input a vector of features and the weight of each feature. Okay, it's just it's the same way to represent what we've already talked about. Instead of doing x1 w1 plus x2 w2 is basically the dot product. So this is x1 times w1 plus x2 times w2 plus x3 times w, so on, and the bias. So this is the simplified way to sort of represent linear regression and linear regression models. Next slide. Next slide. Next slide. Okay. So at this point, do we have any questions? Questions? Okay, I guess we can take a minute-long break here before we delve into the math. I'm going to hand it over to Beckett, who's going to be doing a mathematical deep dive. So I hope you guys have fun with it.
We'll just take like a 2-minute break. We'll get things set up, and then we'll get into all the math stuff, and then we'll have a code at the end, and then the coding portion for the day. Yeah. Do we just try using the dongle so that he can disconnect this computer from the screen? Chart? This one.
Let's give it a go.
We this one.
Yeah. Oh, here.
Yeah, this is
That's the bad one.
let's hope this works.
All right. It'll work.
It is really hot actually. There is a thermostat.
Oh, is it? Trying to see. Yay.
Is anyone else feeling hot in here? We can adjust the temperature if you have anything. I think I'm
Getting too hot. It just makes can we just try connecting that once and see
For this.
We have a USB-C.
Yeah.
this is a USB. Well, it was right in.
I don't want that on the recording.
We're gonna have to edit this recording.
Yeah.
Just-
Well, it's a relic
okay.
of our.
Yeah, that's. Yeah. I think I may do a slightly also smart break right after the first math portion, got like derivatives and stuff. Because the other like partial derivatives and all that gets a little
Messy. Yeah.
Keep it simple and figure it out. If you want to gloss over something.
Okay. Just
So wait, don't worry about it. We'll probably take them.
this.
Yeah, like slides. It's fine.
Okay, I'll stand.
I'll take a seat. Have
Yeah.
some fun.
Yeah,
Enjoy
you
your
just
first
put my
workshop.
jacket on.
Yeah.
Oh, yeah, yeah.
Are you staying for a bit more?
So we like 10, 15. I think we're on track. We've done it 40 times. Also, just feedback in session. Do you guys think the pace of the workshop is okay? Are you being able to grasp everything?
Okay, well, I give another break. I have to do something else to the slides.
You do?
Angelina and Amma needed me to make announcements.
Oh, wait, that was, I
I'll-
made the census announcement.
Oh, you already made the sense. Okay, there's another announcement that Angelina needs me to make, so. All right, I think we're gonna get started on the math portion now. So the first part of the math portion, we're just gonna be talking about some basic, not prereq, but some basic math ideas that we'll carry on into actually applying it to a linear regression model. So the first one is a derivative. So how many of you know what a derivative is? All right, everybody, cool. So I can speed through this. So the derivative of a function is the rate of change of a function. Cool, we all know that. If the derivative is positive, function's increasing, derivative is negative, function's decreasing. Any questions so far? Cool. Now we will talk about partial derivatives. And so we know that the derivative is the rate of change of a function, but partial derivatives will deal with functions with multiple variables. So in this case, if we have like a function that takes in two inputs, right? F of x comma y, how do we represent the rate of change of this? And we can do that with something called a partial derivative. And so here's what a partial derivative does. It basically says, let's say we want to find the rate of change with respect to the variable x. So how is this function changing as x changes? What we're going to do is we're going to basically calculate a regular derivative, but any variable that is not at x gets treated as a constant. All right. So that was a lot of words, but hopefully if we go over this example, it will make a little bit more sense. So when we're taking the partial derivative of 2x plus 3y squared, so we're taking it with respect to x. So all the y's just become like constants, right? So nicer way to maybe write this is like 2x plus 3c squared, where c is a constant. So what is the derivative of a constant? Anybody? 0, right? So now we get the derivative of 2x plus 0. Derivative of 2x is just 2. So that's how we calculate partial derivatives. And so with y, we substitute all the x's with c's. So we get 2c plus 3y squared. 2c is a constant. Derivative of a constant is 0. 3y squared, the derivative of that is 6y. So do we have any questions on like calculating partial derivatives? The speed okay? Okay, cool. Yep, what I said. All right, cool. Now we're going to calculate something called the gradient. So all these fancy words basically mean we're going to calculate the partial derivative with respect to each of these variables. So with f of x, y, z, we have to calculate the partial derivative with respect to x, with respect to y, with respect to z. This is a typo. These should actually be partial derivatives. All right. So if we have like x, y, z, a, b, c, we would have like 5 values in this like vector right here, right? The partial derivative with respect to x, y, z, a, and b. So in this example, this is our function x sine y plus 2z cubed, right? Partial derivative of x, this is a constant. Sine of y is now a constant, right? Sine of a constant is a constant. So derivative of x times a constant is that constant. So that's how we get sine y. Derivative of sine is cosine. So x cosine y, and then we just, this is all now a constant, and we do 2z cubed. Any questions on how we get a gradient? So a gradient is basically, you can think of it as like a list of partial derivatives with respect to each of those variables. Okay. Now, you guys get to do a question on your own. What is the gradient of this? I'll give you like maybe like a minute or two, and then we don't have candy today, but I will pick on somebody to answer. Claire didn't have candy. All right. Anybody know what the right answer is? A? Yeah. So can anybody tell me why B is not the right answer? Not the right answer. It's not a vector, okay. And C and D, they just did their derivative stuff wrong, I assume. All right, any questions so far? Okay, cool. That was all the boring math stuff out of the way. Now we get to talk about the actual math related to linear regression. So we had a couple questions about like how we're determining correlation between like weights and our features and stuff like that. And so this is basically what that question is asking. How do we know how accurate we are so we can improve? Remember, if we have really bad weights that are not representative of our data, we're not going to get a good result. So this is a way that we quantify how bad we are doing. And this is called mean squared error. And so basically, well, this function is called mean squared error. There are different types of functions, and those all fall under this umbrella term called a loss function. And a loss function is basically how how do we measure how inaccurate we are, and how can we use this to improve, right? So we'll be focusing on mean squared error. And so basically what we do is we take y sub I, which is our expected value. So the right answer, for example, versus our predicted value. So whenever you see the little hat, it means it's our predicted value. And we square those. And we do that for all of our samples, right? We predict each one and we calculate how far off we are. So that's what that summation does. It just means, hey, do it for all our samples. How far are we off with respect to everything in our data set? And we divide it by the number of samples, right? So hopefully you can kind of understand why we're getting like mean squared error, right? We're squaring our error and then we're kind of averaging it out. So that's how we get mean squared error. Any questions on what all of these symbols mean or mean squared error as a whole? Okay. All right, so this is the entire idea that we were still talking about before. So the loss function is dependent on our predictions, right? Y hat. So if we recall from like a couple slides ago, we have like y hat is equal to like weight 1 times x1 plus weight 2 times x2, so on and so on, plus a bias, and that gives us our prediction, right? So that is this statement, and then the loss function can also be thought of as a function of weights and biases, right? So basically what's going on here is we're basically simplifying y hat of x, and we're just putting it in as y hat of I, right? So really what's going on is all of this gets plugged into this right here, into this mean squared error function. So that is basically what that statement is meaning. We don't write it like that because it gets too cluttered. Any questions so far on how mean squared error actually like correlates to our weights and biases? Because that was a little confusing, but basically we're just plugging in our like linear point slope form equation into the mean squared error function. All right, cool. So yeah.
Does the expected value stay true?
So y sub I is our expected value. This is our predicted value, right? So the expected value is like the right answer. Think of it, right? So it's like with Numan's example of where it's like, how well will I do on my midterm with all of these inputs? Maybe you get a 93 and your model predicts it's an 83. So what this does is it says the difference between the actual value and the value that our model predicted is 10%. And then we kind of do that for all the samples. Yeah.
That is clarify that you square the error so that they can take the count of like positive or negative.
Yeah, that is why we square the errors.
In that case, why not test with the
Why don't we use absolute value? That is a good question. I do not know the answer to that off the top of my head. It is something that I do have documentation for, and I can link you that documentation. But one of the biggest reasons we do square it is we don't really care about whether
What's the question?
the difference is why do we square it instead of taking absolute value?
Oh, because when we square it, we usually get a continuous function which is differentiable at every point. So if I take the absolute value, that's not differentiable at 0. Well, that's the only thing.
Yeah, we forgot about that. All right. Do we have any other questions? All right. Yeah, we will differentiate this, and I will do that by hand too. Okay. So we've covered this point. Our loss function is a function of weights and biases for our model, right? So remember, a loss function is how far off we are. And so what do we want to do to make our model more accurate? We want to minimize our loss, right? And so basically what we're going to do is we're going to use this loss function to update our weights and biases to make it more accurate, right? So the smaller our loss function value is, the better our model is doing, right? So this line is really important right here. So we need to find the weights for which the loss is minimized. And so that's where the entire idea of like going over partial derivatives and derivatives comes in, because how do you find like a local minimum of a function or global minimum? We take the derivative and look at that function. So on the whole, we're trying to minimize loss so that our weights are the best possible that they can be. Cool. So we do this through a process called gradient descent. And this one is like a little bit, basically you're starting at like a really high point, right? And remember, we're trying to find the smallest value possible. So in all of these examples, you can see that it's tending to the lowest point in this space, right? So with this, kind of comes down here, which is our lowest point. And in this example, we start off at a highest point and we once again come down to our lowest value. And so gradient descent is the process by which we can bring a point from all the way up here, all the way down to the minimum value. Yeah, so when we solve gradient descent, we get the values of our weights and biases that give us the smallest loss value, right? Which means it's more accurate. So we use kind of gradient descent to get our most accurate values for our weights and biases. Does that clarify? Cool. Any questions so far? All right, so we will start off with like single variable gradient descent and then get into multivariable gradient descent. So in this case, f of x is a function of one variable, x, right? And so f prime of x is the derivative, which indicates whether the function is increasing or decreasing. We've been over all of that. So what does gradient descent exactly do? If f prime of x is increasing, the function is increasing. So what does that mean? If we were trying to find the minimum value and our function is increasing, do we want to keep going in that direction? No. So we're going to actually go in the opposite direction. And if f of x is decreasing, that is the direction that we want to be going in, right? Because we are tending towards a minimum value. So that is the entire idea of we want to subtract something. Well, we are subtracting a value from the function. And now, so if f prime of x is negative, we want to decrease f of x, so we increase the value of x, right? So in this quadratic curve, we have a negative slope on this side, which indicates that we're decreasing our value. So we want to increase the actual value of x that we're looking at. For example, on this right-hand side where we have a positive slope, the function's increasing. So we want to decrease the actual value of x that we're plugging into our function. So far, so good, or should I repeat anything? All right, so if you're gonna write something down, this is it, because this describes what gradient descent basically does. If f prime of x is positive, so our function is increasing, we want to subtract from x. If f prime of x is negative, which means we are decreasing, we want to add something to x. So basically think of it as traveling in the same direction as decreasing or the opposite direction of increasing. Do you have a question?
Oh, and just like minimizing that difference, mean like the graph. You want to find the value of x that gets closer to 0.
Yeah. So basically which value of x gets closer to 0? We can see that that is 0 here in this case, but if we start up here, it's kind of determining which way should we go, right? Because like if we go back to a couple slides before, if we're given like this really weird function, it can be pretty hard to determine in which way we're supposed to go, like through a mathematical standpoint, and that's why we use gradient descent. All right, so we were talking about how do we update our value of x, and we use basically the derivative, right, to update our value of x. So this is the formula. We say x is equal to x minus alpha multiplied by f prime of x. So basically, why do we have a minus sign? Because we want to go in the opposite direction of what we want to do, right? So imagine if our derivative was negative, we would be adding something to x, right? Which is what we want. If our derivative is positive, we want to subtract something to x, which is what we would be doing. And alpha here is something we call like the learning constant. And so the best way I think to think about this is, let's say your derivative gives you like a -2 value, right? So if you were to say alpha is 1, you would basically move over to the right 2 values. But let us say we want to move over more than 2 values for a derivative value like that. We can just scale it by a constant called alpha, right? So the higher our alpha value, you can think of it as like the greater the changes we have. The smaller the alpha value, we make more incremental steps towards reaching this goal right here. Okay. Any questions so far? All right. Now we get into multivariable gradient descent. So when we were talking about the gradient, that triangular notation from 5-6 slides ago. So the gradient descent is the direction of steepest ascent, right? So what does that mean? We're going in the increasing value of the function. So when our entire purpose is to minimize loss, we're going to want to decrease the value of this function. So we're going to go in the opposite direction of the gradient. And that is what we call gradient descent. We don't want to go in the same direction as the gradient, go in the opposite, and that's how we get gradient descent. Any questions so far? Cool. All right. In Numbin section, there is like this entire like vector notation where we're using matrices. So that kind of comes back here just to make some notation much easier. But x is now a vector, so we have x1 through x sub n. And then our gradient is also now a vector, similar to what we were talking about before. And we're taking the partial derivative with respect to each of those variables. And now we can think of whenever we're doing these operations, think of it as it getting applied to each like value in the vector, right? So for example, what happens here is for like x1, we subtract alpha multiplied by this value right here, and we just update x1 like that. Does that make sense? All right. So this is just a notation thing. Think of it, we're just applying each thing for each x1 value, x2 value, and so on.
Yeah.
Just to clarify, in this case, the function f of x is the loss.
So not yet. The f of x function is these are our, is it the loss? No, it's our predicted values, right? So when we,
If you're trying to minimize it,
so
if we're trying to get close to 0, wouldn't that be the loss?
My bad. Yeah, we do want to minimize f of x. F of x is our loss. Yeah. So x is the features, and then f of x here is our loss function. All right. So once again, this is the entire idea of gradient descent in like a multivariable setting. We're trying to find a global minimum. So we're basically going to the lowest point in our graph. All right. So we are minimizing the loss function. Our weights are W1 to Wn, and then we have a bias B. And then we need a gradient so that we can update these weights and update these biases. All right. So far, so yeah.
Is there a case where the loss function has multiple drops? And if so, how do we know where it is?
Yes. So that is one issue with gradient descent. We can get stuck in something called a local minimum. And that is why I kept stumbling on that word. Every time I said local, I had to change it to global. So the idea is you'll cover these ideas in advanced track. We won't touch on them in beginner track, but there is an idea called momentum. And so the idea is, imagine you have a ball rolling down a hill, right? If you give it no momentum, it's going to stay within that hill. But let's say we give it momentum and that hill is like a local minimum. What it can do is it can go over that hill and over and then continue exploring, right? So that is one of the ways that we can minimize our chances of getting stuck in a local minimum. But that is a very real issue with gradient descent. We do get stuck in local minimums. All right. Any other questions? Cool. All right. So this is the part where we actually look at the gradient of the mean squared error function. And you don't need to know the derivation, but will briefly gloss over it. If you look at our slides, there's a link to a very mathematically thorough derivation of this, but we'll just quickly go over it. All right. Okay, can all of you see? Okay, cool. So, sorry, my handwriting is not the best on iPad, but this is our mean squared error function. And what we want to do is we need to minimize it according to our weights and our biases. So what we're going to do is we're going to take the partial derivative with respect to each weight and with respect to our bias, right? And so that would look something like delta L. Right. And then, all right. So that is what we are going to try and calculate, these two values right here. Okay, so the first question that we are going to want to answer in the process of kind of getting to the solution is, what is y hat in this case? Does anybody remember what y hat is? Yeah, it's our predicted value. And so what is the formula for our predicted value? Yeah, so it's basically all our weights times x plus the bias. Right, so more specifically, y hat of I right, so we're just looking at like the I weight, the I feature to get. All right. So what we're going to go ahead and do is we're going to take the partial derivative first with respect to the bias, because you guys cannot see the slides, but it is slightly simpler. So what we're going to go ahead and do is this. So that is what we're going to first calculate. And so what happens when we kind of take the partial derivative as summation, we can just put that inside. So 1 to m. Right, so that is what we need to calculate now. And what is the partial derivative of this with respect to the bias? We may have to apply chain rule. We didn't go over chain rule. Well, remember that there is a b in here, right? Y hat has a b. So this is where this is why I wanted us to define y hat. But if we look at this, I equals 1 m. Remember, that's what y hat is. So we can't just say this is a constant value quite yet, because there is a b inside the squared value. So what that means is we have to apply chain rule. And what happens is we get like 1 over m, I equals 1 m, 2 times and then we take the partial derivative of what is inside. So basically you take the derivative, like assume like all of this is just a big C, take the derivative of that, and then take the derivative of what's inside. Once again, you don't need to know this derivation. It's just for some people who are interested. Yi is a constant, because remember that is our expected value. So we're not really calculating our expected value. We're just plopping it in from some table. So it's not really dependent on anything that we are trying to like calculate the derivative with respect to, right? So that is why we don't care about yi. It's just a constant here. So even here, xi is also a constant, right? It's not changing with respect to w. In this case, w and b are not necessarily constants. All right. So remember that y hat is this plus b. And so basically based on our partial derivative or derivative knowledge, we know that w and x have no relation to b. So that is a constant value that goes to 0. And then the partial derivative of b is just 1. And so what we get is like 2 times this times 1. And so the minus are you talking about this minus? that is a typo. So we get this. This basically a -2. And so I won't go through the same process for differentiation with respect to W, but if you do look at the formula, W has like this extra xi. So when we pull back the slides, you're going to see that the formula for the partial derivative with respect to B and the partial derivative with respect to W are different because W actually does have this constant xi sub j. So this was all just explaining where that x sub I comma j is coming from because it just pops out of nowhere. And it comes from the fact that y hat is like this representation of what it actually, like it's an entire function and we're just plugging in that function, right? So we need to consider what is that function actually computing. All right, any questions about this? You don't need to know this, by the way. It's just for people who are interested because we've gotten that feedback before. All right. So that is how we are getting these values. I is the ith training sample, J is the feature that we are looking at also. Okay, so we were talking about this idea of like line of best fit, right? And so minimizing our loss function is like finding the line of best fit, right? So in our line of best fit in this example, you know, we have like X and Y values. X has like M in this case, which is a weight, and it has an intercept, which is our bias. So which values will get the least error, right? So basically which ones will provide like the least difference between all of the points in our like scatter plot. And that is our line of best fit, right? So you minimizing loss is like we're finding the line of best fit for our curve, right? So which kind of straight line matches all the data points the best. Any questions so far? All right, cool. So I think 1 or 2 workshops ago, we talked about how we have to train a model, right? And so we are kind of going to get into that today, and we're going to define like with a little bit more rigor what training a model actually means. And so how do we train a model, right? Is it fair for a model to train on data? Be tested on data it has already seen? Any ideas? Is it fair for a model to be tested, like for its accuracy to be determined on data it has already seen? No? Okay. Do you guys have a reason for why it would be? Yeah, so we generally don't do this because of 2 reasons, right? One, if we select a subset of our data and it trains on that, it has already seen it. So it already has fine-tuned itself to that data, right? But when we're looking at a model, we need to think about its real-world applications too. So it'll be training on data it has never seen before. So what we generally like to do is we like to split 2 things. We have a train set and a test set. So the training set is what the model trains on, and the test set is kind of what it gets tested on. Think of it as like a midterm exam for your model. Your professor will probably not give you all the homework questions on the midterm, right? The idea is he wants to see how much you actually learned to be able to apply, you know, what you've learned on the actual exam. Any questions about that? All right, so this is testing our model, right? So what we're gonna do is we have our test data and we have all of those features. We're gonna feed all of that input and those data points into our model, and we're going to get its predicted value. Then we know the true value of what it should be, and we are once again going to calculate the loss between our predictions and the true values. And now we still use the loss function to tell us how well we did. So the loss function kind of serves as 2 purposes. It tells us how well we're doing or how bad we're doing, but it is also used in the training process, right? So the only difference here is we're not updating our weights and biases on this data that we've seen, right? Whereas when we're training with something, we basically do all of these same steps, but then we update our values. With testing, we don't update our values. We want to see how it's performing, right? Because if we update our values based on this, this is basically now a new train set. And to be clear, you can use your test set as a train set. You would just have to get a brand new test set, right? That is not the same as anything you've trained it on. So any questions about how we test a model and the difference between like a train set and a test set? Yeah. So here's, I think, the best way to explain it. So when we're looking like at our loss function, it minimizes across all of our samples, right? So the idea is, let's say you are 0.1 off on like one example, and then you are 20 points off on another example, and you train your model, and this is what happens. You are now 0.5 points off on your first example, because you change your weights and biases, but now you're only 0.3 off on your second example, right? And so the idea here is we may not always produce the best predicted value every time. Like if we think of like this idea of a scatter plot, if we want to have a straight line, there is no straight line that will connect all of these points, right? Does that kind of answer your question? It's not necessary that it produces the exact predicted value. We're just trying to minimize the difference between those two. Sometimes it will produce, but on a general basis, we're minimizing the difference between those two. And because we have to do it for so many different samples, it's not generally possible that each sample will produce the exact predicted value with linear regression. Any other questions about training and testing models? All right, cool. Now we get to do a Kahoot. Naman, do you have the link?
It should be in the notes.
All right, let's see.
Oh, shoot.
Wait.
No,
You know what? Let's disconnect this for a second.
give us a sec. We'll figure it out.
Are you okay if I accept cookies? It won't let me click anything.
Good idea, good. Yeah. It's just
Continue. There we go.
gosh, it's like that's why I just like sped right through that right now.
Post this Kahoot live with friends. I think we can do it. Yeah, we can do it. Should I do team mode? Teams on your personal device.
Get up to 2 teams.
Do we have that?
Mm-hmm.
Do you have to pay it?
No, I think we should do this. Just like have people. All right. Maybe we should just wait. Is that premium? I think so.
So yeah, that's
Oh, teams on a shared device. It is.
yeah.
All right. Sorry about that. Wait, I couldn't see. had to play it on my computer because our older devices will not have any memory. So I'm put Kahoot music on my computer, put it on that table, and just play it on full blast.
So funny. At least it's like actually matching this time.
It was bad. I used to like whenever we had to like expect questions, I'd run over and log in, forget sometimes. All right. We have the Kahoot link up, the code. It is team mode, so basically 2 people on a team just go with one device.
I see there are 9 people, so who's the lower one?
Naman will join you.
Winners. Very confident, I see.
I've never seen
Are they gonna be that crazy? Like, oh. I mean, I looked at it briefly. I remember like some of the questions being a little like crazy, or some of the answers rather.
Oh yeah. Yeah, what does AI do? Programs robots that take over the world. Murderous AI robots. That's what we're here for.
Cheat on exams.
2, 4, 5. All right, I think everybody is in. So we are going to go ahead and start.
What is a hypothesis in this context? Where's the music?
Just
Where is the music?
Oh, it's
Are the winners winning?
that's
That's the real question.
yeah.
Who are the winners?
all right, a theory.
Yeah, true, but context matters. So
Ooh.
First,
Hey, who became that? Oh, we taught that last.
yeah. Why do I think CNN the news channel every time I hear that?
why does the music keep that?
It's because it's like not part of it. It's team talk right now, and then it's gonna start.
I personally think it just
I mean, it does just
someone
now.
did that. Okay.
Yes, it is all knowing. Yeah, that's the thing. You can't be too quick. Let's see.
Well,
Oh, living up to your name. I see.
okay, we have winners winning. Come on. Because it is cool.
Hey, let's go. It's close in the top 3.
There are only 7 questions.
Be careful on this one.
All right.
I warned you.
The person who put red, it's more efficient just means how fast it runs. Minimizing our loss function does not mean it runs faster, just makes it more accurate. All right.
Good. Claire's trying to calculate.
Wow.
Wait, why is that right? Wait, I think it's supposed to be yellow, isn't it? Isn't it? Yeah?
Because here's what we did when we were making this quiz, okay? We decided all the yellow ones are going to be random stupid answers. But someone decided to mess with them. Since everyone is wrong, it doesn't really matter. But yeah.
Yeah.
We can live with this. Yeah.
Yeah, we're the
If you were right.
we're the silly ones in this case.
Whoever picked green, this is your pass. Congratulations, you left
All right.
again. Oh,
What?
feature.
Oh.
Feature. Does anyone not like people? Why?
What? No.
Does anyone not like it, you said, or like it?
Like it.
Oh, yeah.
Hey,
Like people.
you. Why don't you like B plate?
I like to fill myself up. And I'm vegetarian, so all you really get at B-plate is leaves.
He's not wrong.
All my vegetarian friends
I
will
feel
prefer
like a
those.
goat
Really?
and not the goat I want to be.
Okay. Yeah. I usually go to B plate for breakfast.
I mean-
Lunch and dinner is like mid, I think, but yeah, that's it. Yeah, like you get hits, you get misses, but also epics like that too. So
Still variability to put me out.
okay. Linear progress, progressing up.
There's not a single funny one.
Targets will cause features to
I
decrease.
told you yellow will never be the answer. And you still
yeah.
Yellow.
Yeah. Yeah, it might be a flipped order there. I think it,
Targets don't change the number of features.
yeah, but the features will change the target, right? Yeah, exactly. All right. Number 3. Linear progress. 2. E. And go Jaden. All right.
Look, winners, whoever you are, if you did it for the memes, good job. Because you came last.
All right. All right, are we good with
Yeah,
Yeah.
we're gonna jump into ethics after this. We're
Take
jump,
like a 5-minute
with
break.
the, let's
Yeah.
take a break. What we're gonna do now is an ethics portion, just discussing ethicality of AI, because that's something that people discuss all the time now. And then we're gonna jump into a coding segment, which I don't think you should miss. You'll basically gloss over some pre-written code and understand how a linear regression model is coded out, because that's essentially what you'll be doing when you start taking ML courses and you go into advanced track. So it's just to get an intuitive idea of what certain functions mean, of what certain libraries are. And we definitely have more workshops in the future. I think workshop 6 is primarily focusing on the libraries about machine learning. So we will have a more, I would say, a code-focused workshop towards the end, and we'll have a guided project at the end. But yeah, at this moment, just try to get an idea of what's going on if you have any questions. But we'll take a break for 5 minutes now. If you have any questions, feel free to ask. And yeah, I will be heading out. If anyone wants to connect, my name is Navan. Just shoot me a text. I'm on the Discord all the time. But yeah, I will see you guys next week, hopefully.
You're not. He's not. I don't think any three of us are gonna be here next week, but.
Wait, next week? No way. Hold up.
Maybe Wade's gonna be here.
I might.
I spoke too soon.
Let me check that real
What's
quick.
the one where I spaced it out?
I think we were changed. Yeah, I think we changed it up. Let me check.
We have 7 officers taking one track and we have 3 officers for workshop. So we
Um,
split up so that you can be exposed to different ones. If you think that someone taught you a concept that you really liked it, you can feel free to go to them. We're all super active on the Discord. So I will see you guys.
Yeah, just to update you guys, I will be here next week, so you can look forward to that. All right, actually, yeah, 5-minute break, right? Yeah, all right, so let's take a break. I know. I mean,
The derivations on there are not that.
I know. I'm a math major, dude. We talked about too much math. Okay, to be fair, I am taking 2 math classes this quarter, and it kind of sucks. Yeah. One of them we're actually doing like gradient descent in class. We're doing like the actual like. It's fun.
Really?
Well, okay. You'll
How
you'll learn. Okay, you'll. Oh wait, someone's calling you. I think. Is that? Accept? Or who's?
Oh, who the hell is that?
I don't know.
It could be, I'll just accept.
Okay, I've got.
Hello? Okay. Oh.
Invitation by Discord.
Yeah. Let me see.
No,
Okay.
no, no.
1 second, because I know it's like not. It's not
What up?
right. So
Yeah, I completely forgot about it.
let me figure this out. Invite.
Yeah, reason why I don't remember that.
Copy link. Okay.
Yeah.
Okay. How would you like me to send it to you? Can I just like send
Email.
invite?
Oh, share.
Share to
AirDrop.
AirDrop? Okay, and then which one's yours?
We're really good on time today, actually.
We're doing good.
All right, I do.
Oh, I got it.
Okay.
Thank you so much.
Angela, you need to make an announcement, so I'm just gonna do that.
What's it on?
Some,
Is it like some random thing?
by the way, nope, that's not. Why? Just do blank. Oh. You know what? I'm not the digital design person. That's
Like as long as like when we announce it, there's like. Yeah, that's the other thing. Like, it's just it's like 2 minutes. You're gonna ask it, and whatever. I mean, it just isn't like too much. It's just right.
All right, before we get started on the ethics portion, oh, I'm being recorded. All right, there's an announcement that I have to make, not only me. AI Labs, a not so technical workshop, Thursday, February 9th, 2023, it's hosted by Events at ACM AI, and it is a not so technical workshop, an introduction to AI. Message the events people on Discord if you have any other questions. This is not, I don't know exactly what they're doing, but definitely go check it out. Cool.
All right. Or
Bye.
Yeah. Take care. There you go for it. I guess also one other cool thing I wanted to show a little bit is this single variable gradient descent calculator. So if you want a nice visual on gradient descent, this sort of gives a good idea. So it starts here and then it goes down, as you see, and it really gets so that's just to give you a visual. The link to the calculator is here. I'll leave it up for a few seconds if you want to copy it down. You can try different functions, see what it looks like. This might help later if just to really wrap your head around what's going on. Okay, so now, would you like to right there? Okay, so now we're going to talk a little bit about ethics. Obviously, I know it's not quite as exciting as the technical portion or just the idea, but it is important to talk about because AI is a very, very powerful tool, but it's also a tool that used incorrectly can cause great damage. And so we're going to talk a little bit about privacy. Next slide. All right, so some of the challenges that are associated with privacy and AI include data persistence, which is when the data lasts longer than the person who initially. But basically, for an example, if say like if you get a survey and you enter your information and they say it's only going to be used for one study, but then they wind up using it down the line for some other purpose, or for longer than you thought it was going to be used for, then that's data persistence. And I kind of covered the other point, data repurposing, for used for a different purpose than it was originally collected for, same sort of idea. And data spillovers, the data includes basically data from people who were not the target of the data collection process. So an example of this is, say, you want to do some sort of study for college students, but you hand in US Census data. That includes all, like basically, I don't know if it's all Americans or all American adults, but it's definitely more than just college students. And those people that are not college students that are in the rest of the data set, they have their data recorded, but they were not the people that were, they're not the target for whatever we're using the data for. Next slide, please. And a reason why this is important is that ML and AI models often depend on large amounts of data to get accurate results. And in order to acquire that data, certain data collection methods can often intrude on privacy. And as an example, a US tech company, Clearview AI, recently violated Canadian privacy laws by collecting photos of people in Canada without their consent, and they allowed law enforcement to match those images against their database. So yeah, this was data that was taken without consent and it was used against them. So these are definitely issues that AI faces. So it's just something to be aware of.
I'll just mention one thing. Also, this is a little bit more recent with the data privacy stuff, but we talk about this idea of like consent, where if you give your consent, they have access to data. Consent may not actually be such a clear line. So recently we had like OpenAI and then Google Copilot within the past year kind of come up, and they actually deal with a very different type of consent because they're pulling from like open source repositories and stuff like that, right? But the issue here is intellectual property and consent of giving that intellectual property out becomes an issue, right? So whenever we're thinking about like consent, we have to be a little careful because consent can mean like a lot of different things. So in this case, it's quite literal consent of like getting your picture taken. In other cases, it can be like consent of like giving your intellectual property or not even citing your intellectual property if somebody else uses it. All right, yeah, cool.
And for the last part of our workshop, we're gonna do a bit of a coding example. So I'm gonna leave the link up here for a few seconds so you guys can copy it down. Okay, I assume. Okay. Oh boy, okay. Nobody saw that mess of code. Oh, get back. Okay, this link up here. That, oh yeah, you have to, sorry. It'll be officially 10 more minutes, but
Yeah,
I'll try to get
so-
through it.
If you can't see the button that says like open with collaboratory at top, you need to sign in first.
All right, you think 10 minutes will be?
Yeah,
Yeah, okay.
this is a very short coding course.
Yeah, so this isn't very long. We might not even take the full 10 minutes, so. All right, so this is a linear regression. So these are just a bunch of libraries. Are we covering this later in the?
Yeah, so we'll cover some of these libraries later. We'll mainly be working with like NumPy, and NumPy is just like a math tool library that we use.
Yeah.
And all of these fancy libraries are just used for linear regression, so that
Yeah.
we don't have to implement all of our derivative fancy stuff like that on our own. So you don't need to worry about those libraries. We'll have a workshop that goes into all of those later.
So yeah, we're just gonna run that. Oh, what? Okay. Yeah, if it gives you that warning that's not authored by Google, just hit run anyway.
You can trust us.
Yeah,
We don't
we're,
have a tendency to hijack.
yeah,
That's not our job, okay?
yeah. I don't know. Yeah. I think
don't do that.
I think there are,
hope.
yeah, I don't know. I think there are maybe I don't know. Okay. Yeah, you can just trust us that we're not going to hijack any of your data. Just take our word for it, please. Okay. Anyway, so yeah. So for this, this is just some pre-processing data. Right here for. I assume that's the people after us. Anyway, so this is just, so this is the num data. This is, so we're generating 300 numbers and we're going to generate them. So np.linspace, all that does is it generates basically the way it is, it generates 300 random numbers from 0 to 50. It actually generates num data, but as we see here, it's passed 300 is passed in via num data. And noise is what basically it creates it's the randomness. Yeah, I'm not great at explaining it, but yeah, this creates the function basically. Yeah, so and then this splits in processes the data. What all this is doing, all this code is doing is we're going to plot the data. That's what we're going to do in a minute.
And the first block is just into random data points.
Yeah,
Yeah.
we're generating a bunch of fake data. So
Yeah.
this basically generates a bunch of random X values between 0 and 50. 300 random values, 300 evenly spaced values between 0 and 50. Okay?
Evenly spaced.
Evenly spaced.
Yeah.
And then what this does is it generates 300 random values that we then multiply by 50 and add to all of our existing values in this function. Right? So we basically multiply our values by 4 plus 14 and plus a bunch of like random values so that we can create this nice scatter.
And finally, we present that scatter. And this is what we get. So as we see, it's actually pretty tightly correlated. Oh, yeah. So yeah, so as we see here, this is the graph that we just created. This is training and testing data. Now what we're going to do is we're going to make a linear regression model. So the model linear regression That's from the library, right? The,
That is from the library.
okay. Okay, yeah, so then we run that. And now we're checking the model's parameters. So we're checking the weights and biases of this linear regression model. So as we see weights, so the bias here, that's the y-intercept, right? And the weight is that's just the slope, right? Yeah, so that's the slope of the function, this model, this line that we're making. So now we're going to evaluate our model on our test data. So model score, I assume that just like evaluate, that does the mean squared error, right? Yeah. So this model.score function, this is the function that actually runs that mean squared error thing that Venkat was talking about earlier. So now we're going to run that. So as we see, it's 0.917, which is pretty good. Right. It's all right. It's all right. So it means it's 91.7. Yeah. So this means that it gets it right. Like 91.7%. Yeah, that's right. Yeah. It's my first time. So anyway, so yeah, it's getting it right 91.7% of the time. And that's all right, but I think we can do better. So now what we're doing is we're going to compute the loss of the mean squared error loss on our test data. And when we do that, we get 312. So what's that supposed to mean?
So remember when we were like doing like mean squared error, how we're calculating like how far off all of our values are, you know, with each data point? This is kind of that average value. So what we're doing is we basically create all of our predictions, right, using your model, and then we plug in our actual like results versus the predictions that we made, and we do that mean squared error formula. So far, so good. Any questions about that?
All right. So now what we're going to do is we're going to plot that best line, that best fit line. And with that, we get this. So this line here is our model to predict basically our prediction. And all these points here are fake data. Now we're going to run a real data set with more dimensions. So, so for this, this is a similar kind of thing. I'm just going to run this because this is the fit model. And then we're checking the model parameters. So now what we have here is various different factors that contribute to possibly having diabetes. I don't know what each of these mean, but is it safe to say that if it's like a greater absolute value, that it's a stronger correlation? Yeah. So if we have if we look at something like this, negative 3.86, relatively speaking, it is a negative correlation, but it's very weak, especially compared to something like this, which is 632. That means it's a much stronger correlation and it's positive. So basically, if it's a very high positive number, that means it's a very strong positive correlation, very large absolute value, but negative means very strong negative correlation. Yes?
So let's say that you're doing something with your regression, right?
Yeah.
How much of this do you really need to know versus pulling from previous models, pulling from skeleton code? Do you know what I mean? Right? Like how much are you typing from scratch versus how much are you grabbing from skeleton code?
Yeah. Right now we're just showing, because the code this workshop doesn't assume prior knowledge of Python. We're just covering the basics of how machine learning works. And so what we're doing here, we're not really focusing right now on getting the specifics down of like how to code all of this. We're just teaching you how, like basically what's going on at a higher level. All right, so now, and then the model bias, this is the y-intercept that we talked about before. And now we're going to evaluate it. So as we can see, it's not as good. 0.52, 0.5288. That means there's not as much of a correlate. The line of best fit isn't actually that great. And now we're going to compute the mean squared error loss. And as we can see, that's also much higher this time. And there we go.
Yeah, I just have like a question. Does anyone have an idea of why like our line of best fit is kind of like worse in this higher dimensional data set? Like any ideas? So earlier we had like about like 92% accuracy, when we just had like one factor, but as soon as we go to like a higher dimensional space, like our accuracy like depletes, and there's actually an issue called like the burst of dimensionality. Like as you increase the number of dimension your data has, like as you consider more and more features, like data points in space tend to be like further away, and it's actually not proportional. So like in 1D they might be closer by the Euclidean metric or whatever than in 2D, like if you were to like draw them. So like basically points get further away in higher dimensions, so linear regression kind of breaks down in higher dimensions. Yeah, and also just to elaborate on your question, generally all of this is done through like the library, right? You see, we're not like implementing like mean squared error, gradient descent, and all of that. We just usually have to copy, like we have to call the library and call the functions that that library has. The reason we like to go into like the depth of what's going on is, for example, if we started this workshop off with just showing you model weights, you won't really know how to interpret those model weights or have any idea on like why you're getting those model weights. But when you go out into the real world, you may get model weights you don't like, right? In our example where Nandan was here and he was like, playing too many video games has a negative correlation with your midterm exam score. You know, what if your model gives you a positive correlation? You need to be able to figure out why and kind of like trace through that, right? So in most cases, you'll just have to use the libraries, but it's really helpful to know how it actually works in case something goes wrong.
So is this a little bit more in depth than your 2 to 3 training with this?
Yeah, if you were to code up like this actual solution to like the diabetes problem, you'll probably use like a library which does most of the things for you, and all you input is like basically like a vector containing your data, for example. Like the number of bedrooms in your house. Like if you want to predict the price of a house, you would just enter into like a linear regression model to the features like number of bedrooms, the size, things like that, and then the model would just like behind a black box learn like the weights. You wouldn't have to like print the weights or anything, and it would just like train the model, and then we can just like test it on your data. So it's actually like maybe 4 or 5 lines if you actually want to use linear regression on a data set, but this is sort of like the intuition behind linear regression, and any deep learning model or architecture you work in the future will sort of involve the same process where you first like look at the data set, like what kind of a model can I use on this data set, and then you look at the correlation in the data set, and then you split your data set into like a testing data set and a training data set. You train on the training data set and you test on the testing data set. So that's the basic pipeline that we kind of want to demonstrate.
And kind of mentioned about the difference between the artist score and the mean squared error. So the artist score, the line of best fit is on error, and then you use that line of best fit to predict that, so we get the mean squared error. That would get the more.
Okay. So what we can add on, R2 score is almost like a percentage, like it's almost like how good your model is. So the 0.52 out of 1 is like 52%. The mean squared error is actually not something that someone who's like improving the model looks at, because this is like an internal thing that the model uses to improve its own like weights, like its own slope, its own intercepts. But the mean squared error, so because like if you increase the number of data points, for example, in your data set, instead of calculating the error for more data points, the mean squared error will be higher, but that doesn't necessarily mean that your model is performing most right out. Yeah, so usually if you want to like see how well your model is doing, you look at R2 score or the accuracy score. There are different metrics people use for different types of problems. And mean squared error is more like an internal thing that the model uses to tune its weights. So we kind of wanted to show it to you just so that you get like an idea of what it looks like.
So if the number is like greater than something that's a model.
Yeah, so if the weight, for example, if the error is like really large, then the model would be like, oh shit, I'm like doing really bad in this data set. I need to correct myself like a lot, so it will make like major adjustments to weights and biases. But if the error is like small in magnitude relatively, then it'll be like, okay, I'm doing relatively fine. I'll maybe like do this slightly here or something. Just the rough intuition.
So the value does show like it's a good stuff like that.
Yes, the R2 score. But not the mean squared error. That shouldn't be taken literally.
Yeah, mean square error has to be kind of taken like a context.
Yeah.
This is like when we're talking about like recursive dimensionality, if you have like that's the exact reason why this mean square error is so much higher, right? Because you know those points are so much farther away. So it doesn't necessarily mean that our models like in this case it is performing worse, but it doesn't necessarily always like imply that. But if you take it within a context, right? Like if you were to change the biases and weights, and then it jumps up or jumps down, then you can compare. But you can't just say like there's no like standard cutoff.
Or a training function like the code like gradient to some extent minus. Or like how a gradient.
Yeah, so that should happen in training call. Wherever you fit, yeah. When you fit, that's when you apply gradient descent. So one thing you will find out is that linear regression has a closed form solution, and you've like shared that with them already. Okay, so basically linear regression in like any amount of variables, you can like you have like a set algorithm in math that you can use to calculate the best weights and biases. But the thing is in more complicated models like neural networks, logistic regression, which is the next topic, there is no closed form solution, there's no mathematical way, so the model has to use gradient descent. So the gradient descent would happen in this call, where it's used looking at the training data and try to like memorize the trends in the training data. Yeah.
So does it use the mean squared error to like retrain the model?
Yeah. Yeah.
Keep running it over and over.
Yes, you will see in like a future workshop. Yeah, in the gradient descent workshop.
There'd be a lot of trial and error.
Yeah, it is pretty much like trial and error for the model. It's like you can kind of imagine like you can draw this error is maybe 300 right now for like the current weights and biases of the model. You can kind of like plot like maybe put the weights on the x-axis, for example. You can imagine putting the weights of the model on the x-axis and then plotting the error. So you'll notice that for different permutations of the weights, like for like different slopes and intercepts, for example, the error would be different for the model, right? We generally want to be at the lowest point of that, like imagine like this like imaginary landscape. So that's what we learn about the gradient descent. That's a great question.
Any other questions?
Yeah.
No?
Yeah, so like if you were to plot plot a function, like a function takes in a weight and it plots the error. So like it maybe so for example, you could like have a function which takes in a slope. So let's say that f takes in a slope and it takes in an intercept, right? That is what that in logistic regression we try to find a slope and intercept, right? So whenever we draw a line of best fit, it has a particular slope and intercept value. For that particular slope and intercept value, it will generate like an error value, right? So you can kind of imagine like drawing the error on like some kind of like chart. So like the error would vary with like how your slope and intercept is changing. Does that make sense? So like changing the slope slightly might change the error, like might reduce it. Like if you could go this way or you could go up. So in in gradient descent, basically what we do is we learn how to like descend the slope of any like in linear regression, it's easy to descend the slope down here to like a minimum. But in like more complicated architecture like neural networks and convolutional neural networks, it's harder. So gradient descent like tells you how to descend down the slope.
Because we get like add this right there. So yeah, and there could be different ways to get this error, like different methods for that error. This is like a generalized version of it.
And with a lot of weights or slopes, then it would like multi-iteration. Is it? Or is that?
Yeah, so in our case, if we have like one input feature, we would have like just one slope. But if we had 2-3 input features, like number of bedrooms in our house or like square feet, And then we had like multiple slope values, but for each feature, you would want like a particular weight assigned to it. Like how much does that weight matter, you know, and you just keep that.
Just like you mentioned, like the learning rate for the media. And so that at the start, they didn't put the learning rate for not. And then also the minimum like that.
Yeah, that's actually a very advanced concept. It's called decaying learning rate. So basically the intuition is exactly that. Like initially, like you might be somewhere far away, like your loss is high, so you want to take big steps. So you maybe like take big steps, but then like as you go closer, your learning rate should be smaller. Like initially you want to maybe take like big step, like hop here and come down here, hop here and come down here. But as you reach like a minimum, you want to kind of slow down. So yeah, we do use like a decaying learning rates, but that's a very advanced concept. So we will cover that.
Yeah. And that also comes back to the idea of like momentum, like so that we don't get stuck in like a low voltage. We don't get modify the voltage. All right, any other questions? Cool, I think we finished the coding portion. Thank you all for coming. I believe like 99% sure that there is a workshop next week. So it was my fault. I forgot to send out the message that there was no workshop.
Oh, I'm so sorry.
You guys can blame me for that. So 99% sure there is a workshop next week. I think the like schedule, like weeks corresponding to workshops is also on the Discord. So if I am wrong, which there is still a chance, please refer to that. I'm so sorry about last week, but thank you all for coming out this week. And next week is I think logistic regression. But yeah.
All right.
All right. Yeah.